Alright, in this video we're going to look at some more prerequisites for college algebra. So specifically what we're going to look at is a couple examples of simplifying radicals, some operations with polynomials, so combining like terms, a little bit of multiplying polynomials, that kind of stuff. And then we'll finish things up with some factoring, so factoring greatest common factor, and then we'll get into factoring trinomials. So the first thing we're going to look at is simplifying radicals. And so the idea with that is you're going to try to factor out the largest perfect square. If it is a perfect square like number 1 here, the square root of 36, we just go ahead and do that and say that's 6. That's it. We're done. But we can do other things like in example 2, what if we have a negative in the front and then take the square root of 36? Well, if it's on the outside, you can think of the square root as like a grouping operation, and so we go ahead and take the square root first and then apply the negative, so that just makes your answer negative, so that's just negative 6. Okay. However, what if we put 2 negatives in there, and if we take a square root of a negative, there's 2 possibilities for us. Whether we are accepting complex numbers or not. At the beginning of class, we're just going to say it's not a real number, you're going to get a complex number. So I'm going to give you the 2 different answers. So we can't take the square root of a negative, that's outside the domain of the square root, and so this is not a real number. You can try to put that in your calculator, it'll tell you domain error or something like that. Okay? However, later, we'll go ahead and look at that in a different perspective, so we can rewrite that as negative 36 times negative 1, and then we're going to use a little fact. Well, this is kind of what I end up doing. Now, we have to be a little bit careful here that this is essentially what we're doing. So the square root of a times b is the square root of a times the square root of b, and so we were going to find the square root of 36, and we're going to find the square root of negative 1. That's essentially what we're going to be using here with this problem. And so you do have another negative there, so you have to be a little bit careful. You got the negative on the outside of the problem right here. I'll go ahead and make it yellow right here and here. That's just going to make your answer negative. So the square root of 36 is going to be 6. The square root of negative 1, that's going to give us the I, and then you have the negative on the outside, which is going to make your answer negative. So there's your answer's negative, so we get negative 6i. Okay. So let's look at another one. Let's just do the square root of negative 36. Now, at the beginning of the class, we're just going to say that's not a real number, but later on, we'll go ahead and do essentially the same thing we did in problem number 3. The only difference is this one doesn't have a minus sign in front of the square root. So we'll just get 6i for this one. So later on, we'll say, okay, well, square root of negative 36, that's the same thing as 36 times negative 1 under the square root, and that's going to give us 6i. So that'll be a little bit more important later on. And we'll go ahead and look at one more example here, example number 5. No, 2 more examples, excuse me. And so the first 4 problems, we were doing some variation of 36. Now we're going to look at 72. The difference here is 36 is the perfect square, 72 isn't. And so the cleanest way to do this is figure out what's the largest perfect square that divides evenly into 72. So we list all the perfect squares as, I think I go up to maybe 12 squared is 144. Okay? And I'm going to place where 72 fits in that list, and I want to find the biggest one, 64 and down, that actually fits into 72. And so I can just try to divide them. I can do 72 divided by 64. I'm going to get a decimal. 72 divided by 49, going to get a decimal, doesn't go in evenly. So then I try 36, and it's 36 times 2 is 72. Okay? I know what the square root of 36 is, it's 6, so we'll be able to change that into a 6. And then we don't know what the square root of 2 is, so we just leave it alone. It's too bad. 2 just has to stay in there. So that's how we write it, is 6 square roots of 2. And that's as far as we can go. If we're doing some sort of application, maybe we want to convert that into a decimal, but for us, we want to leave this. This is what's called the exact form. 6 root 2 is the exact form. The decimal form, you need your calculator for, or some other technique for approximation. All right, let's look at one more. So we have 4 times 150. And so 150 fits right after 144. The next perfect square would be 169. So we'd have to try perfect squares before 150. It turns out that 25 is the largest. 25 times 6 is 150, okay? Now when we simplify it, you got 4 as a factor hanging out. The square root of 25 is 5. And then poor square root of 6, we don't know what it is, so we leave it alone. 4 times 5 is 20. 20 square roots of 6, that is your exact answer. Okay, so where we're going to use this, we'll do some problems with quadratics where we do quadratic formula and completing the square, and we also have something called the square root method where we'll use this and want to simplify that. That's coming up pretty soon. Okay, so moving along, we're going to look at some operation with polynomials. So we'll do, I think, one example, just kind of doing the distributive property of some sort, combining like terms. We'll talk about a little bit of degree and a leading coefficient as a little bit of a mini review here. So operations with polynomials. We'll do polynomial division a little bit later on in the semester. I think it's in the 3rd unit, maybe, or maybe the 2nd unit. I think it's the 3rd unit, so it's a little ways away. Okay. Operations with polynomials. So we're going to look at, I think probably the instructions would be something like simplify or whatever. So here's what we got going on. And of course we follow the order of operations, but the problem is x and minus 5. Those aren't like terms. Like terms have to have the same variables with the same exponents. We can't do that. Everything in the second parentheses is also not like terms, so we can't combine anything. So the next thing to do is to go ahead and do the distributive property. So we have 2 separate parts. We got the 2x to distribute, so we'll do that first. So 2x times x, 2x squared. 2x times minus 5 is minus 10x. Okay? That's the first part. We're done. Now we're going to look at the second part, and we're going to distribute the minus 3x squared all the way through. So minus 3x squared times 4x cubed will be minus 12. X, and we add the exponents, x to the 5th. Minus 3x times minus 11x will be 33, and then x squared times x will be x to the 3rd, and minus 3x times minus 9 will be 27x squared. Sorry, minus 3x squared times minus 9 is 27x squared. Okay? The next thing to do is to combine like terms. Like terms have the exact same variable with the exact same exponents. And I'm going to go after the largest exponents first, and we're going to write it in what's called descending order. So the first one is x to the 5th is the largest one, so negative 12x to the 5th. I don't see any 4th powers, but I do see a 3rd power, plus 33x squared, x cubed, excuse me. And then the x squareds, we have a 2x squared and we have a 27x squared. So how we combine them is we add the numbers and keep the variable 29x squared, and then we got minus 10x by itself. Okay, and so we're going to talk about something else here, just as an introduction of some vocabulary that hopefully you've heard before. The degree here is going to be the largest exponent if we're looking at one variable polynomials. So the degree here is going to be 5, and then attached to the largest term here, sometimes this is called the leading term, which I just circled. The leading term is negative 12x to the 5th. The 5th power, that's going to be the degree. And the leading coefficient is the negative 12, the factor attached to x to the 5th. And sometimes that's going to be important to us a little bit later on. It will tell us some information about the polynomial. Okay. So we'll look at another one. X plus 5 and then 2x minus 3. Now this one's different than the previous one. Here we're multiplying 2 binomials. There's 2 terms. Terms are separated by plus or minus. So the first term is an x. The first 2 terms are x and 5. The second one is a 2x and a minus 3. Those are the 2 terms in each one. And so how we multiply it, you may have heard of something called FOIL. It's basically just the distributive property. So x times x, that's going to be the first times the first. That'll be 2x squared. Then we're going to do the outer, x times minus 3. And that'll give us minus 3x. Then we'll do the inner, 5 times 2x. It's 10x. And then we'll do the last, which was 5 times negative 3, which will be negative 15. We do have like terms to combine. That is the minus 3x and the 10x, which will make 7x, and then minus 15. So we're not solving it or anything like that. That's it. Don't do anything else. This is a degree 2 because the x squared is the largest term. On the x squared is a 2, so it's 2x squared. So the degree is 2, and also the leading coefficient is 2 on this particular problem. So degree is 2, and leading coefficient is also 2, by coincidence here. Okay, we're going to move on, and we're going to do 2 more examples of multiplying some. And this time it'll be a binomial times a trinomial, and then we'll go ahead and do an application. So a minus b quantity times a squared plus ab plus b squared. And then you'll go ahead and distribute that a all the way through. Now the order when we multiply doesn't matter. So here I'm going to write the a first and then the b. You can certainly put the b first if you like. So if I do negative b times a squared, that's negative b a squared, but I can go ahead and write it as a squared b to keep it in alphabetical order, okay? And so stuff's going to cancel, so you got the a squared b and the negative a squared b, the a plus b squared, and the negative a b squared. So those are going to drop out, so you're going to have a cubed minus b cubed, and then we have a special name for this. We call it a difference of cubes. Okay, so that all, most of it drops out, and you get a cubed minus b cubed. We call that a difference of cubes. And we'll go ahead and do an application of this, and we're going to factor something. So you're going to take something from a cubed minus b cubed and write it as a minus b times a squared plus ab plus b squared. So we're going to look at 8x cubed minus 125y cubed. This is rigged nicely. 2 to the third power is 8. 5 to the third power is a 125. So that tells us the a will be 2x. So a cubed would be 2x quantity cubed, which would be 8x cubed. So we got a good match there. B we'll say is 5y. B cubed would be 5y quantity cubed, which is 125y cubed. That looks perfect. So we can rewrite that as a cubed minus b cubed, which factors into a minus b and a squared plus ab and plus b squared. So we know what a is, we know what b is. So we'll go ahead and we'll install that into the formula. Be a little bit careful about the a squared. It does need parentheses around it, and probably parentheses around the a times b just to help us out with that multiplication there. Okay, and so we got everything there. So last thing to do is go ahead and kind of simplify things down a little bit. So the 2x quantity squared is 4x squared. 2x times 5y is 10xy. And then 5y squared is going to be 25y squared. And that's the thing completely factored out. We won't run into this a whole lot in this class. I think we have a few homework problems on it. You know, if it's something you guys really like, we can do some on the homework, but probably won't test you on it. But if you're moving on to pre-cal and further, then it's something you'll want to know. Okay, we do have another one we'll look at, a plus b quantity times a squared minus ab plus b squared. And so we'll go ahead and multiply that out in a very similar fashion. So multiply the a through, and then we'll multiply the b through. And then stuff is going to cancel out just like in the previous example. So after we've done all that multiplication, negative a squared b cancels out a squared b. Positive ab squared will cancel negative ab squared, so those are all gone. So what we're left with is a cubed plus b cubed, and so we call this one a sum of cubes. And we'll do an application where we go ahead and use it to factor a sum of cubes. And usually they'll be rigged pretty nicely. So 64 is 4 to the third power. 27 is 3 to the third power. So a will be 4x. A cubed will be 4x quantity cubed, which would be 64x cubed. b will be 3y. b cubed will be 3y quantity cubed, which would be 27 y to the third power. So our polynomial here looks like a cubed plus b cubed, which factors into a plus b, a squared minus ab, and plus b squared. So just install your parts. A is 4x, b is 3y. Don't forget the parentheses on the square there, 4x quantity squared minus 4x times 3y with parentheses, and then plus 3y quantity squared. We'll do a little bit of cleanup. First factor is all good to go. 4x quantity squared is 16x to the second power. 4x times 3y is minus 12xy, and 3y quantity squared will be 9y squared. So that's our application of our sum of and difference of cubes formula. So we're going to look at a little bit more of factoring in just a moment here. So typically the first thing we want to do when we're doing factoring is look for what's called the greatest common factor. And why we want to do that is it makes the numbers we're working with smaller. We might see something that's easily factored if we remove the greatest common factor, which we will abbreviate. We'll call it the GCF. So greatest common factor we'll call it the GCF. Okay. So we'll do an application here in just a moment. Alright, so we're going to factor 15x to the fourth plus 5x squared, okay? So for the GCF, 5 goes into 5, 5 goes into 15. So that's your greatest common factor for the numbers. Now you have x squared and x to the fourth, so the greatest number they have in common is x squared. So the GCF here is a 5x squared, and so that's what we're going to factor out. Factoring is the exact opposite of doing the distributive property or foiling or whatever you want to call it, and when you're doing those, you are multiplying. So when you do the distributive property, you're multiplying. Factoring is the opposite. So the opposite of multiplication would be to do division, okay? Now, usually you'll be able to eyeball it once you factor out the 5x squared, but here's kind of the work you can think about doing. So take each term, the 15x to the fourth, divided by the GCF, and that'll give you 3x squared, and so that'll give you that missing piece there. Now you can also check by distributive property, 5x squared times 3x squared, well that's going to be the 15x squared, so that looks good. And we could do the same thing with the other term, 5x squared and then divided by 5x squared, and that's going to give you 1. Okay, and then I can check, we already checked that, and then check the 5x squared times 1, that gives us the 5x squared. So you can always check your factoring by either foiling or doing the distributive property like in this one. So let's look at another one. 8x to the 6th plus 20x to the 4th plus 12x to the 3rd. Okay, so the x's are x to the 6th, x to the 4th, and x to the 3rd. X to the 3rd is the most that they will all have in common. 2 definitely goes into all of them. 4 will go into all of them, and I think 4 is the largest for the numbers. 4 goes into 8, 4 goes into 20, 4 goes into 12. I don't think there's anything bigger than that. So that gives us a GCF of 4x cubed. And then we can take each term. We can take the 8x to the 6th over 4x cubed, so that's going to give us 2x cubed. The 20x to the 4th over 4x cubed. That'll give us 5x. And then the 12x to the 3rd power divided by 4x cubed, that will give us 3. Okay. Like the previous example, if I want to check to make sure things are okay, all I got to do is do the distributive property, and I should get back to the original problem there. Okay. All right, so that's one type of factoring the GCF out. The next thing is more of a lead up to actually factoring trinomials by something called a factor by grouping or the AC method. And so it's going to be very, it's the same thing that we're doing here, it's going to look a little different is all. So let's factor 12 and then x minus 11 plus 8 times x minus 11. Now this one's a little bit different, so the factor in common is x minus 11. So we're going to factor that out, and then we'll have to figure out what's left over. We can follow the same convention that we did before. Take each term, 12x minus, you take each term, so 12x and then x minus 11, and we're factoring out an x minus 11. So it'll give us 12x. The other one is 8 or x minus 11, and we're factoring out an x minus 11. And so that's going to give us 8. Okay. All right, so that's all we got going on there. We'll go ahead and look at another example here. It's number 14. We got 2x, x minus 4, and then minus x minus 4. What they have in common is an x minus 4, so we're going to factor that out. Okay, so take each term, 2x, x minus 4, divided by the GCF, x minus 4. We're going to get 2x. And then the x minus 4 divided by x minus 4. That's going to give you 1. And that's it. There is this thing completely factored out. So that's kind of like the one of the big steps in factoring trinomials using something called the AC method. Okay, so that's what we're going to get to here is what's called the AC method for factoring trinomials. If you have another method that works, then go ahead and use your method. You don't have to use my method. You just need a method that works for factoring trinomials. So generically, the setup is you got ax squared plus bx plus c, and I use a diamond to kind of organize it. I've seen other people use a table. Maybe you do it in your head. All of them is the same as you're just finding some way of organizing your thought process. So on the top, you have a times c. On the bottom is b. So what you're looking for is you want to find two factors of a times c that multiply, two factors of a times c that add up to b. Let me rewrite that. Add up to b. Add up to b. Okay. All right, so let's go ahead and factor completely. And we're going to look at 6y squared plus 11y plus 3. Okay. The a is going to be attached to the quadratic term. The quadratic term is the one with the square, so that's 6. The c is the constant, that's going to be 3. So 6 times 3 is 18. The linear coefficient is 11. 11y is the term. Coefficient is 11. Okay. So we're looking for factors of 18 that add up to 11. So what I do is I write down 18. 18 is 1 times 18, 2 times 9, 3 times 6, and I go through the list. I try to find as many as I can, and then I add them up. So 1 plus 18 is 19, 2 plus 9 is 11, so that's what we want. So 2 times 9 is 18, and 2 plus 9 is 11. So that's what we're looking for. Okay, it does not matter which term comes first, whether we put the 2 or the 9 first. We use that to split up the middle term, the linear term, 2y and then a 9y. If we add these together, we get back to the 11y. So we haven't changed the problem. We've rewritten it so it's 4 terms, and we can do something called factor by grouping. Okay. When we do factor by grouping, it's essentially doing the GCF we did earlier, factoring up the GCF earlier, but with two of them. Okay, so 6y squared and 2y, the GCF is 2y. Factor out a 2y, and you're left with 3y plus 1. The second two terms, the 9y and the 3, the GCF is 3. And then we have 3y plus 1 after we factor that out. If you do not factor out the greatest common factor, it will not work out correctly. So you want to make sure you get the GCF there. Okay. So 3y is in common. We will factor out the 3y plus 1. What is left over is 2y plus 3. That is factored completely. So we'll do one more example of the AC method. I do have another video of more factoring, so I'll make sure that I mention that, or you guys can find it on my YouTube channel, more factoring. All right, listen, we're getting pretty lengthy on this video, so I want to do a couple more examples here. All right, so here 2x squared plus 11x plus 5. Quadratic coefficient is 2, constant is 5, that's your A and your C respectively. So AC is 10, and then the linear coefficient here happens to be 11 again. Factors of 10, 1 and 10, 2 and 5. Which one adds up to 11? That's 1 and 10. So we'll split up the 11x as a 1x and a 10x. Then we'll write down the rest of the problem, 2x squared, the plus 5. We'll go ahead and do the grouping. So group. They have an x in common, 2x plus 1. The second two terms have a 5 in common, factor out a 5, 2x plus 1. We have a 2x plus 1 in common, factor that out, and then what you have left over is an x plus 5. And that is factored completely. Okay. We'll probably maybe talk about a little bit of shortcuts. If your leading coefficient is a 1, there's a little bit of shortcut. I'm going to look at one other shortcut. We'll talk about that one in class, and we'll see a bunch of it later on in the class. I want to talk about one that's called difference of squares, though. So if we recognize the difference of squares, it does make factoring a little easier. So difference of squares is going to be a squared minus b squared. And so what you're looking for, if it's going to be a difference of squares, you're looking for only two terms, a subtraction, and then the two terms that you do have are squares, and that factors into a minus b and a plus b. Now if you want to put the a plus b and then a minus b, that's fine too, if you want to switch the order. Doesn't matter. You can FOIL out a minus b times a plus b to verify that that is in fact what it should be. Okay, so we're going to go ahead and do a couple examples. I think we got about 4 examples here, so they'll be pretty short. 3x squared minus 3. So I do have two terms. I do have subtraction, but the 3's are not perfect squares. However, I always want to factor out the greatest common factor. So the greatest common factor is 3, so we'll pull a 3 out, and we'll have x squared minus 1. X squared is a perfect square. 1 times 1 is 1, so 1's a perfect square. So it becomes 3, and then x minus 1, and x plus 1. You can FOIL that out to verify that that is, in fact, what it should be. Okay, number 18, we have 3x squared minus 81. We do have a GCF. 9 goes into both of them. Factor out a 9, 4x squared, and then minus 9. 4 is a perfect square, 9's a perfect square. There's two terms. You see that we factor that 9 out in the front there. We're not going to do anything else with it. It's along for the ride. It's just going to sit there. Okay, so 9, and then to make a 4, you need a 2. To make a 9, you need a 3. So 2x minus 3 and 2x plus 3. That's it. All right, we got 2 more for you. We're going to get a little bit more advanced example. Number 19, we're going to look at 16x to the 6th minus 9y to the 6th. No GCF, but 4x cubed times 4x cubed is 16x to the 6th, and 3y cubed times 3y cubed is 9y to the 6th. So it is a difference of cubes. I'm sorry, difference of squares. Okay, that's it. Excuse me. All right, and one more. We're going to look at 36x squared plus 81. GCF here is going to be 9. Factor out a 9. 4x squared plus 9. Again, you can always check these factoring GCFs out by distributing, so make sure that's okay. All right. The 4x squared plus 9, that is a sum of squares. And so we don't have a factoring formula for sum of squares. So once we've done that, if we run into a sum of squares, we're done. We just leave it alone. You may see the word prime. So after you factor out the greatest common factor, and it's a sum of squares, you're just going to say, okay, well, this thing is prime, okay, and that's it, okay. So sum of squares and does not factor over the real numbers, okay. So, if we were doing this in the beginning, this is what it looked like. 9 and then 4x squared plus 9. Later on, we'll be able to break this down, and it will factor over the complex numbers. So it'll be 9 and then 4x squared plus 9. That's going to factor into 9. Looks like I got it backwards. Let me fix this. We're going to fix this. So 2x times 2x, 2x times 2x is 2x squared. And then the 9 is 3 and 3, but we need the i's there. And later on we'll get into something like this. You can verify it by foiling it out, and then you'd have to use the fact that I squared is -1 there. Okay? So that concludes the second prerequisite video here.